So please join me in welcoming Professor Emery Brown. It's a great pleasure and an honor to have him here as a speaker. Professor Brown has received numerous number of scientific awards throughout his career. He's known as the world expert on statistical analysis of neuronal data, and his work has been considered truly transformative for the field of anesthesia. He's a professor of anesthesia at Harvard Medical School and professor of health science and technology at MIT.
Stefan, thank you very much for inviting me. It's a great pleasure to take part in this educational endeavor. Thanks again for inviting me. I'm going to talk about anesthesia-induced slow delta oscillations, and you'll see why this is going to be important, because they're something that shows up with all the EEG patterns that we have for the different drugs. And I think it's important not to just sort of see these oscillations, but understand them. And one of the key points that I'm going to make, and you'll see it in some of the other talks too, is even though the oscillations may look the same, the reasons they're there might be quite different. So these are just the funding sources that I've had the good fortune to have over the last few years from our National Institutes of Health, my Department of Anesthesia, and also my institutes at MIT. These are my colleagues that I've worked with: Nancy Capel, Shuna Keju, Patrick Purdon, Laura Lewis, Ahmad Eskandar, Sid Cash, and Shenung Cheng. So this is what I'm going to do. I'm going to talk about what I call Breme's principle. Then I'm going to talk about slow oscillations for propofol and ketamine. I'm going to talk about other factors that affect slow delta oscillations, and then I'll have a summary. So let me start with the definition. What is general anesthesia? Drug-induced reversible state where it has antinociception, unconsciousness, amnesia, akinesia, and stability and control of the physiological systems. And one of the points I want to make is how anesthesia works is really no mystery. And what I'm going to be talking about predominantly here is unconsciousness. We're using the EEG as a way to track level of unconsciousness, but other factors in addition to just the anesthetics can affect the patterns that we see. And that's important for us to be able to sort out because the context is quite important. So I want to talk about some experiments which were done back in 1935 by the Belgian physiologist Frederick Breme. So what Breme did was a set of experiments in cats. In the first experiment, he transected the spinal cord from the brainstem at A. And what he observed was a pattern of the EEG that looked like this, what he called the encephal isolator, or the isolated encephalon. And the EEG appeared awake looking. Then in a second set of experiments, he transected the brainstem mostly and cord from the brain, and he saw a set of patterns that looked like this, these slow oscillations. And so that was one of the first hints that told us there's something in this part of the brain that has to do with about arousal systems in the brain. And what we know is now these are where the major arousal centers of the system sit, in between the pons and the midbrain. And so one of the points that I'm going to make is that all the anesthetics have actions in this part of the brain, and as a consequence produce slow oscillations, but they produce them by different mechanisms. So if we look at the EEG like this, we see that perhaps the patterns look different for the different drugs, but an easier way to see them is with the spectrogram. And one of the things you can readily see is that all the anesthetics produce slow oscillations, even though ketamine has a different mechanism from propofol, which is different from dexmedetomidine. So let's talk about propofol and its slow oscillations. So these are the patterns that you see with propofol as you give increasing doses of propofol, going from what is a low amplitude, high frequency oscillation down to a large amplitude, low frequency oscillation, slow oscillations, burst suppression, and then to an isoelectric state. What I want to talk about are these slow oscillations for propofol. How do they come about? So if you're in the operating room, you see this. So the slow oscillations, slow delta oscillations, and the alpha oscillations here. And then if you look at the neurophysiology, you can see that there are inhibitory interneurons everywhere. And we know that propofol acts through GABAergic interneurons, and basically they enhance the inhibitory capacity of these neurons. So in the cortex, in the reticular thalamus, which is an inhibitory net around the thalamus, and also here in the brainstem. But let me just point out this one particular set of circuits here in the brainstem. The preoptic area of the hypothalamus, which I'm pointing to here, actually projects onto the arousal centers here in the brainstem. And these are all GABAergic synapses. So when blood comes through the basilar artery and hits this part of the brain, you can see that it's going to turn off these arousal centers. And this is going to be part of the way that the propofol induces its slow oscillations. It also acts directly in the cortex and also directly in the TRN. But we can apply Bremé's principle and know that part of the effect has to be right here in the brainstem. And the anatomy supports that, 100%.